going to be a reaction mixture. So let's take a look at the general. Let's see, there it is. The general procedure here. You know, we try to do it stepwise if it's possible. Stepwise or simultaneous, preferably stepwise. In chapter 17, you're going to have to do this preliminary step, which is going to be solution, dilution. Is this solution, dilution? Just do this. Keyboard. So we take a look, what is the mixture? If it's a Henderson-Hasselbalch mixture, then we'll just use that equation, skip the ice table. And that can happen in any of these steps. So step 1, we might not have a Henderson-Hasselbalch, but by the time we get to step 2, it might be a Henderson-Hasselbalch mixture, like in titrations, etc. And then we just keep adding the steps. Normally, we start off with the largest K value of the species that are present. And then when we have reactions, you know, we have to remember, like, strong go to completion. And so some of these Ks we have just memorized. So recall that strong reacts to completion. In other words, we say K is very large. If K is very large, then we just go all the way. Sometimes we make this assumption. This is, in effect, kind of resetting. You know, when we reset, we just shift the reaction 100% in one direction. Even if the K is not so large, we can reset it and then let it re-equilibrate. Like, for example, if we reset it forward, we can let it re-equilibrate backwards as well. It depends on how big the K is. So, in a sense, this is kind of like resetting, you know, with that large K value. Okay. All right, so let's take a look at some example mixtures. Here we could do, let's say, a strong acid plus a strong acid. So let's take something like this. What would happen? All right, let's take 6 molar HCl and 6 molar nitric acid and mix them together. And so in this particular example, we don't have to necessarily have amounts, but we can have some amounts here. I'm going to take 50 milliliters, and then I'll take 50 milliliters of this. And then when I mix them together, I'm going to get a total of 100 milliliters of mixture. And typically, this is going to be an HCl-HNO3 mixture. Typically, we look for 2 things. You know, one would be the inventory. 2 would be the pH. If we're only interested in the pH, then we might handle it a little differently than the inventory. The inventory we could get with or without the pH. You know. And so here, the preliminary step we always do is step I, the solution dilution. So what we need to do is we need to calculate the new concentration of HCl for the reaction mixture. This is pre-mixture here, and so for the mix, I'm going to just call it HCl for the mix. What is the concentration? So the concentration is V initial over V final times the initial concentration of HCl. So V initial is 50 milliliters, V final is 100. As long as you have the units the same, they cancel. So it's a 50 to 100 dilution. This is what we call the dilution factor. The dilution factor, we can just reduce that to 1/2. So it's a 1/2 dilution. So this is a kind of a dilution we can do in our heads because it's just 1/2 the initial concentration. The initial concentration was 6 molar, so this is just going to be 3 molar. If you look at the HNO3, do you see the HNO3 will have the same dilution factor? It's a 1 to 2 dilution or 50 to 100 dilution. And so in the mixture it should be at 3 molar as well. Alright, then we do our step 1. Our step 1 is the strongest acid plus the strongest base. That's the most likely reaction. So what is the strongest acid and what would be the strongest base in this case? Well, they're both strong acids in water, and so it doesn't matter which one you pick, they're equal in water. So we'll just pick the HCl. And the strongest base? Water. What is K for this reaction? You have to have these memorized, the K values for the strong acids. Very large. So initially we start off at 3 molar, 0 molar, 0 molar here. And when the K is very large, we just assume it's complete reaction. So essentially we're going to reset this whole thing to the right, so that we end up with 0 molar here, 3 molar, 3 molar. Now, if we were to double check our K here is infinite, because, or actually, what is our K? K is products. It would be 3 times 3. It would be 9 over reactants, which is 0. And so the K value is 9 over 0, which is going to approach infinity here. And how large is very large? Is very large infinitely large? No. Very large only turns out to be like 10 to the 15, 10 to the 20th, something like that. And so they don't match. They don't match, but it's okay. This is good enough for us. It's good enough for us because if we were to actually do, there is actually quantitative K value here. The concentration residual HCl is so small, it would be negligible. You'd have to have a huge amount of water to see any HCl molecules present. Good. Let me put that in quotation marks. It depends on who you talk to, of course. But that's what we're going to do. All right, step 2. What's the next strongest acid? Is it hydronium? No, it's not actually hydronium. You know what the next strongest acid is? Nitric acid. And what's the strongest base present? Water. And so if we take nitric acid and water, we're going to make hydronium and nitrate. K for nitric acid is also equal to very large. Get rid of this. So what we need to do here is we need to pull down the hydronium that was made in step 1 down into step 2 here. And so we're going to start off with 3 molar hydronium from step 1. And then we have the 3 molar nitric acid initially here in the mixture. Now, don't get confused because I use initial here, but I use mixture here. So this initial is the initial for the mixture, not the initial for the very beginning, pre-dilution. And so this is the initial for the mixture, not the initial for the HCl here. And so they don't match. Let me write a little note. For the reaction mixture. So the change, when you have a K that's very large, what is the change going to be? We assume it's complete. I'm going to have 0 molar nitrate. So at the end of this, we'll have no more of this. We're going to have 6 molar H3O plus and 3 molar nitrate. Shoot. To add pages. Step 3, what's the next strongest acid present? Yeah. Water, or actually it's also hydronium. Let me turn this on. Hydronium is also a strong acid, but if we did hydronium, this is what's going to happen. Hydronium and the strongest base present? Water. And hydronium plus water makes what? Water and hydronium. So this is incorrect for step 3. Because nothing changed. And so we go on to the correct step 3, which Mitchell has right. It's water. Water is going to be the next strongest acid. What's the next strongest, or what's the strongest base? Not the next strongest. Strongest base present is water. So this is Kw. This is going to produce hydronium and hydroxide. Now, do you think, well, what I have to do is, I have 6 molar hydronium. So I'm going to carry that down here, if I can. And so I'm starting off with 6 molar. Do you think I'm going to add any significant amount of hydronium? Will this change the pH at all? Not at all, right? Not at all. But will I add a significant amount of hydroxide? And the answer is yes. So H2O is pure liquid, so we ignore that. And so we're going to add an insignificant amount of hydronium because the initial amount is so large, it's 6 molar. And so X is going to be insignificant compared to 6. However, compared to 0, anything's significant. You know, and so the analogy here would be like, you know, one drop of water in the Pacific Ocean is nothing. But, you know, one drop of water on the moon would be huge. You know, if somebody found a drop of water, although it'd be frozen. Although in the sun, it'd probably be vaporized. In the shade, it'd be frozen, probably. And so this is the same thing here. X relative to 6 is negligible, but X relative to 0 is significant. So this is why we're doing step 3 for the inventory, because the hydroxide we had none to begin with. And so if we find something, some hydroxide, and this is, you know, how much hydroxide do you expect? This is strong acid. And how much hydroxide do you expect is just from the collisions of the water. Now the collisions of the water are going to be inhibited. Normally how much hydroxide do we expect in water? Normally water has a pH of what? 7, pure water, which means it has a POH of 7. And so normally we expect 10 to the minus 7 molar. But because we have so much hydronium here, Le Chatelier's principle says it's going to try to push it back to the left. And this push back to the left, we're going to generate much less than 10 to the minus 7 molar hydroxide. Much, much less. But it's still going to be significant. And so we're going to get 6 plus X here, and then X. Now, here the K, again, this K, obviously you have to have memorized. What is the K at 25 degrees C? This is going to be the total hydronium times the hydroxide. And so this is going to be 6 plus X times X. And here the simplifying assumption, I think, will work very nicely with 6X. So we'll have to do 1/6. So at 0.2. And 1/66. So this is going to equal, X is going to equal 1.66. I don't have that many sig figs in my concentration, so I'll just do 1.6 times 10 to the minus. Bigger, make this smaller, 15. Is that right? So the SA is justified here. I mean, 6 plus that is just going to be 6 molar here. It's such a small change. However, it is a significant change compared to 0, so I'll write that in here, 1.6 or 1.7. Yeah, I need to round that up. Actually, I need to round it up to 2, but it's all right. I'm going to carry one extra digit. So let's double check this. If I rounded it to 2, it's not going to work out. It's going to give me 1.2. If I only have 2 sig figs, let's see what it comes out to. 6 times 1.6. It comes out close. It comes out to 0.96 times 10 to the minus 14 if I round. If I don't round, then it's going to come out to 1 times 10 to the minus 14. And so it depends on how much you want to round this. Officially, we only have 1 sig fig. And so this, it's going to be off. K is going to equal 1.2 times 10 to the minus 14, but this is round off error. And so normally when I calculate the K values, I use the unrounded. And so versus a K, let's just, I should have kept that in my calculator, which I'll just put it back in there. Yeah, versus a K if I just kept the digits in my calculator, which came out to 1. Using all digits. Now, a 1.2 might make you wonder if you did a calculation error. There wasn't a calculation error here, it's just rounding error. Because we're off by 20%. All right, and so what do we have in this mixture? In this mixture, we have no HCl molecules. That's going to be 0 molar. And we're going to have chloride. Chloride's going to be 6 molar. Oh, 3 molar, sorry. Not 6 molar. And the HNO3, this is for the molecules. We'll have 0 molar. HCl is also for the molecules. The nitrate, is going to be at 3 molar. And then H3O plus is going to be just a hair above, 10 to the minus 15 above 6 molar, so 6 molar. And then hydroxide. Hydroxide is going to be at 1.6, or, to the correct number of sig figs, 2 times 10 to the minus 15 molar. This would be the inventory. Now the pH is equal to the negative log of the total hydronium. The total hydronium is just a little bit above 6 molar, so this is going to be the negative log of 6. We're only allowed 1 sig fig, so I'll just carry 2.77, negative 0.8. But really, we shouldn't be using what we call the stoichiometric concentration here. We should really be using what? The effective concentration. When the concentration gets high, it can deviate significantly from the stoichiometric concentration. Things can deviate significantly from the stoichiometric concentration. That's because the probability of clustering becomes more significant. You don't memorize numbers in a table. When you have a table, what do you memorize, if anything? Well, you should memorize something, normally when we have tables. The things I try to memorize, don't always do this successfully because my memory is not so great, but what do you try to memorize?
The extremes.
Yeah, the extremes, right? The so how much do things deviate from ideal? Is there a significant deviation from ideal, or not a very significant deviation? And what does it depend on? What are the two things that the deviation depends on? See, these are the types of things I would write. If I have a table, I'll tell you exactly what I would have written for this table. And it's not a huge amount of memorization. It's very simple. Especially before test, I would have done this. Because I would have it in my notes. The way I studied is I just wrote everything in my notes, and then before the test I would review my notes every day, every day, so that by the time the test came I would have things memorized. because it would take me some time to memorize this stuff. But the daily, it's like a driving, pretty soon. Um, it's just like in your motor memory. Let's see. So this table here, what did you write, if anything, for this table? I don't memorize like the caption or anything. I try to put this in my own words. So in your own words, tell me about this table. And I would just annotate, I'd have like maybe some of the extreme values, since I was doing handwritten notes. I'd just have some of the extreme values and then just write something simple. Something simple would be, okay, when, even when we get to a solution that's only 1 molal, which would be about 1 molar. When we get to 1 molar, even sodium chloride shows about a 10%. This is what I would have done. As I said, even sodium chloride is about 10% deviation from ideal. But it gets much worse, because when you look at lead at 1 molar, it's way worse. It's supposed to be 3, but it's only 1.3. And so I would have said, okay, the charge on the ion, of course, is going to be significant. So 2 plus is going to be much worse. Same thing with 2 plus, 2 minus here, 2 plus, 1 minus. And the concentrations, charge and concentration significantly, and so 10 to very high, greater than 50%. That's all I would have remembered off this table. That way, some people, they say, oh, I need to memorize everything. So if I threw in like aluminum, what would you expect aluminum nitrate to be? Even worse or better? Even worse. And so some people would say, oh, that's not fair, that wasn't on the table, you never said anything about aluminum, But if you know the trend, then you can answer those types of questions. And you often get a lot of those questions where it's not in, it wasn't in the book, it wasn't in the homework, but it's just a simple following the pattern, the trend. And so if you know the trend, you're going to be okay. And so this is what I mean by this. And then if I had that in my notes, let's say weeks ago, and then by the time the exam comes up, this would be very simple. And so that's what I recommend. And so I know a lot of people are struggling with this effective concentration stuff, but you don't want to be struggling with effective concentration right before the test. You want to have this stuff down, and then you're prepared for the test. Let's go back. So that's good, but there's also one more thing, is the charge. And then you want to just have kind of a rough idea of how much is the deviation. Yes, the higher the concentration, the higher the deviation, but where does it make an impact, And so where are these calculations going to be the most accurate? When we're doing, when we're using the stoichiometric we want low concentration. This is why all our concentrations are like 0.1. 0.1's been like kind of the highest concentration we've been dealing with, right? Well, you think 0.1, 0.1's already kind of low, but 0.1 we don't want to go too high because the calculations become less accurate. The calculations become less accurate. It's still okay because it just saves us a lot of work, but we have to remember that this is just approximate. The approximate pH should be about 0.8. We expect some deviations here because of the activity, and so I would have expected some significant deviation here due to the activity. So we could do another example here. We'll do in this case, we'll do a strong base plus a weak base. This is another mixture. Here. We'll just pick a strong base like sodium amide, and a weak base like we could do a related weak base or unrelated weak base. We'll do an unrelated weak base, like sodium acetate. So in the first one, we're going to do a solution dilution that's going to be a little bit more difficult. In this case, let's take 50 milliliters of sodium amide solution, and then we're going to add this to 55 milliliters of sodium acetate solution. And so the dilution factors are going to be a little off, and so this is going to be harder to calculate in your head. We're going to do with 0.1 molar. Now, sodium amide is too strong of a base to exist in water, and so if you try to make 0.1 molar, it would fail. So what we're going to do is we're going to add 0.1 moles of sodium amide to 50 milliliters, or actually 0.1 moles to a liter, and then take 50 milliliters of that. For the sodium acetate, we're going to do it at 0.3 molar here. And so this is going to give us 105 milliliters here. Yeah, the reason we do that is to emphasize, people are okay with strong acids. People are not okay with strong bases. So it's the same thing. When we have 6 molar HCl, are there any HCl molecules there? No. And the same thing here. But the problem with this is it's a salt, and so automatically people will think, okay, the salt will dissociate, and then we'll have 0.1 molar amide. And so I'm putting quotation marks just to emphasize that this is going to be a similar situation to the acid. And you're already familiar with the acid. It's just the base part that screws people up. And so let's figure out the mixture concentration for sodium amide. What would that be? What's the dilution factor here? 50 over 105, 0.1 molar. So the number is not going to come out so clean. And so these numbers are a bit of a pain. And so this is going to come out to 0.476. Now, I don't want too much round-off error. Officially, this is only good to 1 sig fig, so 0.5 molar, but 0.5 molar is going to be too significant. So I'll just round once at the very end. And then sodium acetate, I'm going to abbreviate acetate AC. The dilution factor for sodium acetate? 55 over 105. And this is going to be 0.3 molar. This is going to come out to 0.157. This I call step I. What's next?
For your strongest base and strongest acid together.
Okay, that's normally what we would do, except that we're going to just start off with the biggest K here. The biggest K is that sodium amide is a soluble salt. And soluble salts are strong electrolytes, so they should dissociate into sodium ions and amide ions. And so initially, if we had 0.1 molar, actually it's not 0.1 molar any longer, because this is not the initial, this is the initial what? This is the initial mixture. Not that everybody does it, but you know, every semester somebody will do the initial in the ICE table. And I'm carrying more digits than I'm allowed. All right. We have other very large Ks that are very large. So sodium acetate is also a K very large, but we're just going to stick with this for right now. In my step 2, I have amide, and so you have to recognize that amide is a strong base. So what's the strongest acid present? And so now we'll do the strongest base and the strongest acid. The strongest acid being water. What's going to form here? Yeah, ammonia and hydroxide. So the amount of amide we're going to carry down from step 1. The ammonia is 0, hydroxide is 0. When we have a K that's very large, the change is complete. So we're going to end up with 0.476, 0.476. Amide is not the strongest. It is a strong base. So step 2 is a strong base. Step 3, okay, we're looking for the biggest K. So in step 3, a lot of people skip this. Your book's going to skip this step because it's just automatically, sodium acetate is a soluble salt. It's going to form sodium ions and acetate ions. K for this is very large because sodium salts are strong electrolytes. So the initial mixture concentration for sodium acetate is 0.157. The sodium ion I have to carry down from step 1. So let's go ahead and do that. Carry this down. the acetate will be 0. If K is very large, the change is complete, so we're going to end up at 0 here. Okay, then what?
We also do for water.
Well, we have to do the next strongest base. What would the next strongest base be? This is a base solution, so we're looking for hydroxide producers. Well, we have a choice here. We could do acetate, or we could do what? But hydroxide plus water is just going to yield hydroxide and water, so we'll just skip that one. We could do acetate, or we could do ammonia. Which one has a larger KB? Ammonia or acetate? And so, step 4, so the question is this. Ammonia or acetate? So what we're going to do is we're going to just compare the KBs. We'll do the bigger KB. So the KB for ammonia, we can look that up in the book. It's 1.8 times 10 to the minus 5. It's a common number, so I just memorized it. But acetate isn't so common, but it is actually pretty common because acetic acid is common. And so the KB for ammonia is directly from the book. The KB for acetate we have to calculate. How do we calculate the KB for acetate? KW over KA for what acid? Acetic. The acetic acid is such a common acid in calculation, a lot of people just have it memorized like KW. KW is 1.0 times 10 to the minus 14. You don't have to have it memorized though. Ka for acetic acid is 1.8 times 10 to the minus 5. So it makes it easy to memorize because ammonia is 1.8 times 10 to the minus 5, the Kb, and the Ka for acetic acid is 1.8 times 10 to the minus 5. So you have two numbers for one memorization. But at 3 sig figs, they're different. And so this is 1.7 something, and this is 1.7 a different something. So to 2 sig figs, they're the same. To 3 sig figs, they're different. So I just memorize it to 2 sig figs. Since 2 sig figs is, for most calculations is enough. So which one will we do? Well, it depends. This is going to come out to what? 5.55 times 10 to the minus 10. Yeah. So which one should we do next? Ammonia. So we pick ammonia. So ammonium should produce more hydroxide than acetate, and this is a base solution. Base solution, we look for hydroxide producers. Acid solution, we look for hydronium producers. So what we need to do is we need to drop this amount down, 0.476 down to the step here. The change is not going to be complete here. It's going to be minus, plus x, plus x. We have 0.476 minus x. X molar and x molar. I'm sorry? Oh yeah, we do. I forgot to drop that down too. That's good. Got it, thanks. We need to drop the hydroxide as well. So we're not starting at 0. We're starting at 0.476. And so the Kb is the products, ammonium. On a test, you should, in case that you make a mistake, to get more partial credit, you could write this out. What we're going to do is we're just going to try the simplifying assumption. And hopefully it works. So x is just equal to Kb for this, since everything else drops out. And then we have to justify the simplifying assumption by calculating the percent change. Percent change is also called the percent reaction, or the percent hydrolysis in this case. Since we have a product here to begin with, the percent hydrolysis is going to be less than expected because of Le Chatelier's type. A lot of product there to begin with. It inhibits the forward reaction. And so this is going to be x over the change over the initial 0.476 times 100%. So 1.8 times 10 to the minus 5 divided by 0.476 times 100. Double 0.37. So this is very good. So it wouldn't make a difference. If we solve this using the quadratic, wouldn't have made a difference at those very low percentages. You can try it and see. It's not going to make any difference. But it does make a difference here, so we should factor it in. 0.476 minus point, now I need 4 zeros. 1, 2, 3, 4, and a 1, 8. So this is going to come out to 0.475972, or 982 molar. I don't want to box it. Just yes. Okay. Zero point 0.0476. If that's the case, yeah. If that's the case, then I need to change this. You're right. Rather than redo that, let's do this. Let's make this 1 molar. And this one 0.3, we'll just leave it at 0.3. Okay. Thanks. Then we'll just leave it at 0.476. All right, then the ammonium concentration is just going to be Kb, which is 1.8 times 10 to the minus 5 molar. And then this one's going to be plus, so it's going to be 0.476, and then I need 4 zeros, and then a 1 8. So 0.476018 molar. All right, this is way more sig figs than I'm allowed, but I'm just going to carry all of them just to see what the calculated K value comes out to. And so we'll take 1.8 times 10 to the minus 5 times 0.47618 divided by 0.475982. And so the K comes out to 1.8001 times 10 to the minus 5. So it looks good. All right, what's the next strongest? Now, when we're dealing with base solutions, we look for the next strongest base. The next strongest Kb. And so what should that be? Acetate. So the acetate we're going to have to carry down from step 3. Which is 0.157. And the hydroxide we'll have to carry down from step 4. .476018. So this is going to be minus X molar, plus X molar, plus X molar. 0.157 minus X, 0.476018 plus X. It's going to equal the HAC times the hydroxide divided by the AC minus, which is X over 0.476018 plus X divided by 0.157 minus X. All right, what do you think about the simplifying assumption? Do you think it looks pretty good for this one? Yeah. All right, so let's go ahead and calculate it. We have 5.55 times 10 to the minus 10 times 0.157 divided by 0.476018. I get X is equal to 5, 6, 7, 8, 9, 10, 1, 8, 3. Is that a significant change compared to the initials there? No, this looks good. The percent change is going to be way less than 5%. When something's this obvious, you don't actually have to show me the calculation. I mean, but you should make a little statement here. It's going to be small. All right, so let's go ahead and calculate the new acetate concentration. I really don't necessarily want to do it, but we'll do it. 6, 7, 8, 9, 10, 1, 8, 3. This is going to come out to 0.1569. How many nines? 1, 2, 3, 4, 5, 6, 7 nines. 7 nines and then an 8, 1, 7. So barely any change. I mean, this is going to be 0.157 basically. This acetic acid, yes, that did change significantly. This is 1.83 times 10 to the minus 10 molar. And the hydroxide, did we really add much hydroxide to that? No. I need 10 decimal places. So 1476018 is 6, 7, 8, 9, 10, 1, 8, 3. Now, the situation is, do these new concentrations perturb step 5? So the hydroxide changed. Will that perturb step 5? Significantly? No. This is what we say, negligible change. Does not perturb step 5. I mean, it still did change. So ideally, we should do this simultaneous, but the amount of work that's required for simultaneous is too much. And so what we say is it doesn't really change it significantly, so we're not going to be in very big error. Does not perturb step 4. Otherwise, we would have a headache. If step 5 perturbed step 4, that is, there was a significant change in hydroxide, then we'd have to go back and fix that. Well, let's go back and check. Did I accidentally miss that before? Yes, I did. For example, if I look at step 1, I significantly changed the amount of amide in step 2. So if you look at, I ended at step 1 with 0.476 amide, but by the time I get to the end of step 2, it's 0. Is that going to screw up step 1? There was a significant change in going from step 1 to step 2. Does that screw up step 1's equilibrium? You'd think so, but when we have a K that's very large, we call this a one-way reaction. And so it can only go one way. This is one way. So if the change, this was a significant change here, it does not perturb it. Because whenever K is very large, nothing will perturb it. And so one way, nothing perturbs this. So this is the reason why I didn't even bother paying any attention to it earlier, because we're dealing with large Ks.
Doesn't it just make sense that it doesn't change it, because at the end of step 2 you have 0, and at the beginning of step 1 you have 0? So they're kind of like,
Yeah, right,
they coincide.
right. That too. Here, if you look at the sodium ion concentration, we changed that significantly. We went from 0.476 to 0.633, but it doesn't matter, because if you increase the sodium ion concentration in this equilibrium, let's say if I increase the sodium ion concentration in step 1's equilibrium, will that perturb it? No, it doesn't perturb it. And so I could double the amount of sodium ion, and it's not going to shift this back left. It doesn't shift it back left because K is one way. Does that make sense? We have to make sure that it's only when the K's are small. When the K's are small, then I have to worry about it. So I didn't worry about it until I got to this step, step 5. Because if I look at step 4, the K is small here. And so a little increase in the hydroxide is going to shift this back to the left. But was this, this amount with 10 zeros and a 183, was that really a significant addition? No, that was a negligible addition. And therefore, I'm not going to have to worry about simultaneous. I'm going to carry on with stepwise. All right, now this is a base solution, so what's the next biggest hydroxide contributor? What's the next biggest K? . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So this is going to be step 6. Hydronium, we're going to start at 0, but should we start at 0 with hydronium? Didn't we make some acetic acid? Yes, we did. We made some acetic acid here. We have some ammonium. Ammonium's an acid too. So we have some acid here. We have ammonia, ammonium is a base, ammonium and acetic acid. So should we do the Ka for acetic acid or ammonium before we do Kw? The answer is no. You're right. The answer is no. Why? Why do we ignore those? Ammonium is certainly a stronger base than water. Not a base, acid. Ammonium is certainly a stronger acid than water. And acetic acid is a lot stronger than water.
Is it because the concentrations are so small? It's a basic solution.
Yeah, its concentrations are so small you probably can ignore it. It's a basic solution, right? But the answer is it's going to be redundant. It's going to be already taken care of. In fact, if we did Ka for acetic acid, the Ka for acetic acid describes the equilibrium between acetic acid and acetate. We just did it. We did it in terms of hydroxide. We didn't do it in terms of hydronium because this is a base solution, so it would have been redundant. So even, yes, the concentration is small, so we could have ignored it, but we didn't even have to do that. It would have been redundant to do. We would have been going in circles. And so the general rule, and the general rule is based on not going in circles. The general rule is for base solutions, look for the hydroxide producers. For acid solution, look for the hydronium producers, and that's it. This is a base solution, so the acetic acid and ammonium are already taken care of in the equilibria. And so we're going to add to the hydroxide, and so we're going to carry down the hydroxide from step 5. And that's going to be 0.4760180000183 molar. I'm going to do plus X molar here, plus X molar. We'll have X molar and 0.4760180000183 plus X molar. So Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And this is going to be X times this plus X. Do you think the simplifying assumption should work here? Yeah. We'll just use that, and then we're going to get X is equal to Kw 1.0 times 10 to the minus 14. Divided by 0.4760180000183. 3, 6, 9, 10, 11, 12. 2.1 times 10 to the negative 12. So for hydronium, this was significant, 2.1 times 10 to the negative 12 molar. For hydroxide, this was not significant. And so this is going to be 0.4760180000183 plus 0. Now I need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 1. So I'm going to get 0.4760180000204 molar. So did I double check the K? I didn't double check the K here in step 5. So let's double check the K here. And make sure I didn't make an error. 1.83 times 10 to the minus 10. I should have double checked it before moving on. That was a mistake. Times 0.4760180000183 divided by 0.1569999999817. This is carrying probably way too many digits, but it comes out to 5.548 times 10 to the minus 10, which checks out. Now, if I were to substitute the new hydroxide here, it wouldn't change it at all, 204, so this doesn't really perturb that. I'll get the same K value. Okay, let's double check this K value here. So 2.1 times 10 to the minus 12 times 0.4760180000204. And so this comes right on 1.000 times 10 to the minus 14. So that's good. All right, now what we have to do, that's the end of the line. There's nothing else after that. And so what we have to do is we have to figure out what the totals are. And so the concentration of sodium amide ends up at 0. And so we'll do the totals here. So let me change this color. So amide ends up at 0 molar. Sodium amide, that is. And then our amide gets carried down here, and our amide ends up at 0 molar. Our sodium gets carried down here, and so our sodium ion ends up at 0.633 molar. Our ammonia continues down here. And so the ammonia concentration ends up at that. Hydroxide gets carried down all the way to the bottom. So this will be our hydroxide concentration. Our acetate concentration goes down to here. Our acetic acid concentration stops here, and that's it. Or hydronium. Our hydronium ends up here. All right, so if I had a beaker I actually had to change the concentration because I made the mistake earlier. But if I had a beaker that's labeled 1 molar sodium amide, I'm not going to find any sodium amide in there. In fact, if I'm looking for sodium amide molecules, although this is an ionic compound, there are no molecules, the sodium amide actually comes out to 0 molar. The most abundant species is going to turn out to be sodium ions. I need to change. Actually, it's not 1 molar, sorry. Did I have solution dilution? Yeah. This is 1 molar sodium amide and 0.3 molar sodium acetate. So the sodium amide and the sodium acetate concentrations are 0. That's these kind of ion pair type things. And then we'll just go down the list. I'm not going to go in order here. Sodium ions is 0.633 molar. .6 molar. I'm only doing this to 1 sig fig, just save writing. Ammonia is 0.47 molar. This is just going to be 0.5 molar. Acetate is going to be 0.15 molar. This is 0.2 molar. The acetic acid, 1.8 times 10 to the minus 10. So it'll just be 2 times 10 to the minus 10 molar. The hydroxide is 0.47 molar. This is 0.5 molar. And the hydronium, 2 times 10 to the minus 12. So what is the pH of this? pH, we can calculate the pOH, or we can calculate the pH directly. I'll just do the log of 0.47. pH is 13.7, which is strongly basic. All right. This is the premix. Remember we had to do the solution dilution. And when we did the solution dilution, then the concentrations all changed. And so it really shouldn't label it like this. This is pre. It should be labeled like this. This is the mixture. Initial concentration for the mixture. All right, that was a long problem. So we'll take a break and then maybe we'll do one more problem and then we'll do the lab. Let's take a break. So the previous two calculations were a mixture of acids. So acid solution, basically. So we look for hydronium in acid solutions. And the second calculation was base solution, mixture of bases. So we look for hydroxide producers. But what happens if we have an acid and a base? And so the next example will be a strong acid, strong base. So in this case, do we look for the hydronium producers or the hydroxide producers, or what do we do here? In other words, for acid solutions, we're looking for the largest Ka to the smallest Ka. For base, we look for Kb's. But for acids, we do the same thing, but we start off with largest K, and the largest K will be the strongest acid plus the strongest base. There are two types of calculations we do for this. The first type of calculation is pH. The second type of calculation will be for inventory. If we're looking for the pH, the pH, we just call that a titration. And we can plot the titration out stoichiometrically by plotting the pH versus the milliliters. Normally, let's go with HCl and the strong base NaOH here. The calculations are going to be a little bit complicated because of solution dilution. So normally we'll start off with like 25 milliliters of HCl. Let's go with 0.1. Maybe I'll bump it up. I'll go to 2 sig figs, 0.10 molar. And then we're going to titrate this with 0.10 molar NaOH. In the milliliters, we don't know how many milliliters. It's just going to be, let's say, X milliliters for right now, as it's changing. So in order to neutralize, we see the concentrations are the same. This is 0.1, this is 0.1 molar, and the stoichiometry is this. It's a 1-to-1 reaction to produce sodium chloride and water. All right, this is a neutral salt. Neutral salt is pH 7. Sodium ions don't hydrolyze, chloride ions don't hydrolyze, so the pH just stays 7. And so when we completely neutralize this, the pH should be 7, so we'll put the pH 7 here. And how many milliliters will it take to neutralize it? It'll take 25 milliliters, because they're the same concentration. So we should hit the equivalence point at pH 7. This is just sodium chloride, salt, and water. That's what forms here. But before that, the pH should start low. The pH should start, well, what is 0.1 molar? 0.1 molar, oops, I forgot to record this. Oh, actually I didn't. It's recording. What is the pH of 0.1 molar? Well, that would be 10 to the minus 1, so the pH is going to start at 1. So we start here at pH 1. And we have 2 sig figs, so actually the pH is 1.00, assuming the pH meter is reading correctly and the solution is made correct concentration. Then what happens is we have excess acid. We don't have enough acid to neutralize all the, we don't have enough base to neutralize all the acid, so we have excess acid. Save this before it crashes. So here's the titration. We start off at a pH of 1, and the equivalence point here, when we've neutralized it, is at pH 7. This is just showing what indicators are okay. If you look at phenolphthalein, phenolphthalein is a little bit late. So what happens is, as we go along the titration curve, we hit the equivalence point where we neutralized it, but phenolphthalein is colorless. This is just showing phenolphthalein changes color around pH 9, and so it's a little bit late. And so if we use phenolphthalein as an indicator, we have an error. How much is that error? It turns out the error is so small, people don't really worry too much about it, because in order to go from pH 7 to pH 9, how many milliliters of sodium hydroxide does that take? Well, it's so vertical here, it barely takes any milliliters. And so even though phenolphthalein is going to be slightly late, the end point is not equal to the equivalence point in this titration, that the error is negligible. And so phenolphthalein is okay. What a better indicator would be bromethymol blue. If we used a drop of bromethymol blue, it starts off at yellow at low pHs and then turns to green at pH 7 and then goes to blue at higher pHs. So we're looking for a yellow to green transition, but the problem is it's hard to see the color change. So it's much easier to go from colorless to color, so there's less error involved with phenolphthalein than there would be with bromethymol blue, and the amount of milliliters that we're off by is so small, people don't worry about it. However, if we took a alizarin yellow, alizarin yellow would be bad because we would have a significant error in milliliters if we use that particular indicator here. So all these bars are just showing what are suitable indicators. Some indicators turn color too soon. Bromphenol, methyl red. One indicator turns perfect, bromethymol. One indicator turns too late, and we use the indicator that turns too late, but we could have used these ones that turn too early as well. Like bromephenol blue, we'd look for green, and methyl red, we'd look for orange. But going from red to orange is hard, and then to yellow, it's hard to see. And thymol blue would be way too early because we'd have to be way down here at this pH, and that's well before the equivalence point, so thymol blue is not a good indicator. And so we use phenolphthalein. For a pH titration, the indicator wasn't necessary. We didn't necessarily need that. So we start off down here, and we neutralize some of the acid, but the pH stays low because we don't neutralize all the acid, so we still have excess strong acid. So this is the excess strong acid region. When we get close to the equivalence point, around here, there's very little excess acid. In fact, most of the hydronium comes from Kw. And so here we have to worry about it. It was like remember we did that calculation, 1 times 10 to the minus 8 molar HCl. And 1 times 10 to the minus 8 molar HCl, where did most of the hydronium come from? Kw, water. And so we're in this region, we have to do that weird calculation we did earlier to calculate the pH. And then we hit the equivalence point, which is a sodium chloride. Nothing hydrolyzes except for water, autohydrolysis, so that's why it's pH 7. And then we go into excess base. Over here we have so little base that Kw is the major contributor to hydroxide. But once we get up here, then we're going to have lots of excess sodium hydroxide here, and the pH stabilizes. And so we could do a calculation anywhere on this curve here. And in fact, your book does just that. So let's take a look at what they do. They're interested in strong acid, strong base mixture. So they're titrating 0.100 molar HCl with 0.100 molar sodium hydroxide. They're using 25 milliliters. They have 4 sig figs in the volume, 3 sig figs in the concentration. So we expect 3 sig figs here in our calculations. But anyway, they're asking, A, what is the pH before the addition of any OH? Well, that's just HCl, and if it's 0.1 molar HCl, do you worry much about Kw contributing? No. And so this would just be pH 1. B, after the addition of 24 milliliters. 24 milliliters, 1 milliliter before the equivalence point. And so 1 milliliter before the equivalence point, they're asking. They're asking C at the equivalence point, D at 1 milliliter after the equivalence point. And so what we could do is we could do some different volumes. You can see these volumes here. Now, the way the book does it is they don't do solution dilution. They don't do solution dilution till the very end. Instead, what they do is they do moles. In fact, rather than using moles, which would be 0.0025, they use millimoles. So they take the moles and multiply by 1,000. And so your book likes to use millimoles. You could do either way. Millimoles is a simple calculation. You take milliliters times molarity gives you millimoles. I do it molarity. And so I'm going to deviate from how the book does it and use molarity instead. All right, some of the points I want to hit in this case. So we did the initial. I want to do the half equivalence point. I should have been saving it more frequently. Must have saved it in the wrong folder. In a typical titration, we have more sig figs. I'm just using fewer sig figs just to speed it up. So we're going 12.5, which this is the half equivalence point. And so I do step I. This is going to be equal to 25.0 milliliters of the HCl plus 12.5 milliliters of the NaOH. And so that's going to give us a total of 37.5 milliliters. Of mixture. All right, so let's go ahead and calculate HCl concentration first. What's the dilution factor for HCl?
25 over 37.
Yeah, it's a 25 over 37.5 dilution to 3 sig figs. And the concentration was 0.10 molar. Actually, should I do 3 sig figs? Did I do 2 sig figs or 3 sig figs? 2. I'll just go to 3 sig figs then. Let's just go to 3 sig figs. So let's take a look at it. Well, anyway, this is the start of it. We'll just continue this next time because I want to give enough time for the lab part. We're going to do a little bit of lab. All we're going to do for lab today is we're going to attempt to recrystallize. So take a look and see if you have crystals. What we're going to do is we're going to take half the crystals that you have, and we're going to try to recrystallize them again. But in this case, we're not going to completely dissolve them. We're going to add a little bit of water and then heat them up. And then below boiling, but heat them up close to boiling, and then just keep adding a little bit of water until they dissolve close to the boiling. Okay, then we're going to let them cool down as we did before, you know, and add ethanol and then cool them in ice. So we're just going to repeat kind of what we did earlier. Does that make sense for this slide? So we're just going to attempt to do another recrystallization.